Hi everyone. I'm very happy to be able to be part of this amazing program. So big thanks to the organizers. I think you nailed it. So I'm going to present our work that we do at Institut Optique, south of Paris, on collective light scattering. Okay, so that's what we've heard about this morning in the two previous talks, in free space atomic ensembles. Okay, so we won't have a fiber or a cavity, so it might sound a bit different with respect to what Arno just presented, but as a matter of fact, you will see that we have very, very similar results. Okay? So here is the group. There is a part of the group that maybe you know works on Rydberg atoms, but I'm going to present the work of the two teams that work on light scattering. I don't need to motivate that this is an interesting and hard many-body problem. You just put atoms in free space, excite them with light, and look at what happens. It also has interesting maybe applications in the future in quantum technologies. But again, I guess you're experts on this. I will start a little rough with directly the equations, because this is the master equation that will describe everything that I'm showing in this presentation, and maybe also to keep theoreticians awake in this talk. So the master equation, you know it. It's essentially so it's Markovian. Okay, in free space you can trace out the photons. So you have just a master equation with the dipole-dipole interaction that gives you Hamiltonian and collective jumps. So for instance, if you're an experimentalist and you look at the light scattering, what you measure typically is intensity. Okay, and intensity actually is related directly to the atomic degrees of freedom. So when you measure intensity somewhere, actually you see by this simple formula that the intensity, the radiated field that you're going to measure, is given by atomic correlations. Okay, so experimentally we find it interesting because it tells you that you have two possible probes. Okay, you have one possible probe which is looking at the radiated field, which is precious because measuring this quantity on the atomic signal, I mean on the atoms themselves, is relatively challenging because you have to account for the phase. But you can also look at atomic correlations, look at the atomic degrees of freedom, which will give you information. And in theory, this is what you calculate, and the field is just a near superposition. Okay, so basically, Marcus Greiner-Stolp measured this part, and Arno showed us experiments where you measure the radiated field. And in the group, we have two experiments. One with rubidium, where we have a high scattering rate. We have clouds of atoms that are disordered, and we measure the radiated light. Okay, and we have another setup based on arrays of dysprosium atoms, where you use these multi-electron atoms, exactly like Marcus showed us, where you can access directly the atomic degrees of freedom. I'm going to try to present two pieces of work, one of each. We'll see if time allows. So the first results that I'm going to present were obtained in the vast majority by Giovanni, who was a postdoc with us until very recently on the rubidium setup. So what is the physical system that we have? Experimentally, it's very simple. We use the atomic tweezers that maybe you've heard about that are useful to make quantum simulation. But now we use just one tweezer. We put hundreds or thousands of atoms inside. Okay, so it's a tweezer in the sense that the volume is pretty small. Okay, but we put many atoms inside. So this gives us a cloud of atoms that has very small proportions, very small length scales. So it has a cigar shape like this. Okay, its long axis is about 10 microns. So it's rubidium. The wavelength is 780. So you have about like 15 wavelengths. Okay, but radially its cross section is very small. The typical size is of the order of the wavelength. So the typical cross-section of this cloud is smaller or on the order of the cross-section for one photon to be absorbed by an atom. Okay, so it gives this cloud particular properties in terms of collective emission. For instance, if you look in different directions, you will have very different results. So if you look along the cloud axis and you detect a photon, you cannot know which atom emitted it. There is no way because your cloud is too small. So it means that any photon that's emitted along the cloud is emitted collectively, right? On the other hand, if you look perpendicularly to the cloud, you might be able to resolve which atom emitted the photon, or at least a very small volume. And so typically when an atom is emitted perpendicularly, it's an incoherent emission that's just given by the excited state population. So essentially this means that this cloud kind of defines a mode in which it will cooperatively emit. So it doesn't have a cavity, it doesn't have a fiber, but its geometry defines one mode. It's a Gaussian mode whose Rayleigh length is the size of the cloud, in which you have an equivalent coupling for all atoms into this mode, okay? So you can then actually calculate what this diffraction mode looks like. It's just given by the structure factor of the cloud, and you can define a collective cooperativity, okay? So of course, the single atom cooperativity is much smaller than 1 for this mode, yeah?
During the emission, the tweezer is on, so you...
No, it's off. Yeah, we switch it off because it causes inhomogeneous broadening, but our experiments are fast enough that the atoms don't move. Yeah. So of course, the single atom cooperativity is very small, but if you put enough atoms into the cloud, you might have actually, if you calculate the power that's diffracted in this mode, it's larger than the power that you diffract in free space. So you might have collective cooperativity higher than 1, okay? Another word for this collective cooperativity is optical depth. Okay, so that's the same thing. We have an optical depth that's larger than 1, which means that along this direction, you will have collective effects. And what's nice is that if it happens only in this direction. So you have like 2 modes, one propagating here, where you might have collective spontaneous emission. So we've been studying in the past few years collective spontaneous emission. We've seen Dicke superradiance. We've seen these bursts that Arno showed us with this cloud. We see Dicke superradiance along this mode that is just decided by the geometry of the cloud. We studied the driven case. We actually collaborated with Anna Maria and Derek to try to understand this problem. We've seen also superradiance, just like we saw in Marcus's talk, where subradiance, subradiance, where you see a reduced decay rate at the end of the decay. So you see this curve resembles very much what we saw earlier today. What I want to focus on in this talk for this project is looking at now higher order correlations, if you want, not intensity, but photon-photon correlations. Okay? So let me just explain a little bit what are the experiments that we do. We have the cloud like this, and we pump perpendicularly to the cloud axis. Okay? So this means that we don't have what we heard about before, that the laser does not create a phase that will create phase coherence along the cloud axis. There is no phase coherence due to the laser because it propagates perpendicularly to the axis. So any collective effect that you see will appear spontaneously in the cloud. So of course, if you drive an atom, what you have are optical block equations. We see at low atom number, we see that we have just spontaneous emission, the emission rate that follows optical block equations. So we just see the excited state population. But as we increase the atom number, actually what we see is a very different behavior. If I look perpendicularly, as I told you, there is no constructive interference in the emitted field. I look at incoherent emission, so I measure still the excited state population. So we see that as we drive the system, even when we have high atom number, we see Rabi oscillations in the excited state population. But now if I look along the cloud axis, actually we see bursts of light during Rabi oscillation. When you invert the system, all of a sudden you have a burst of light, okay, that appears and then it goes down and then comes up again. Okay, and this is very different with respect to what you expect for single atoms. So of course, what happens is that you have these correlations that emerge spontaneously in the cloud that enhance the emission in the direction of the superradiant mode. We teamed up actually with Francis, who's in the room, to try to understand what was going on. They performed a cumulant expansion to try to understand this problem. If you do a mean field solution, you have no way of describing what's going on. because if you do a mean field solution, you're never going to create the right phase coherent because we're driving perpendicularly. So they had to go to second order cumulant to actually reproduce properly these correlations. And this is telling us essentially that we have Dickey superradiance while we're driving. Right? These correlations occur spontaneously as we drive, and we have like superradiant bursts that occur as we're inverting the system. Okay, so we have correlations that are starting to emerge in the system spontaneously. We didn't impart these correlations with the driving lasers. Sorry, they appear spontaneously, but then we reach kind of a featureless steady state. I mean, in steady state you measure one intensity, and so what can you tell about correlations is relatively challenging. And so to understand a little bit better whether there are correlations in steady state, what you might look at is then higher order correlations, so G2, photon-photon correlations. You know very well what G2 is. For a single atom, it's an interesting probe because it shows quantum nature of light, or for instance, you have always G2 which is equal to 0 because as soon as you emit a photon, you reinitialize the atom in the ground state, so you never emit two photons at the same time. Yes?
So because in your experiment, without drive, you discovered with mean field, without coolants. So
This?
You emphasize that the distribution between the coolants and this was working.
Mean field doesn't work. You will never reproduce superradiance because the driving laser is perpendicular. Okay?
Yes, but without drive, you can do a normal superradiance like inside the atom.
But without the drive, you have the same problem that, I mean, okay, you could sort of like with mean field, I mean, it's what Arno showed, I think. With mean field, as soon as you put a little bit of phase coherence by hand, then you will reproduce superradiance, I think. But if you start from a full inverted system and don't do anything, mean field will never give you superradiance, okay?
But in this case, you're saying with the drive, you really would be able to out.
Yeah, because the drive doesn't have the phase correlations that you need to have superradiance. If I were to put the drive along the cloud, that's a very different story, and actually mean field is successful there. Okay, yeah. Okay, so experimentally we measure G2 as Arno showed. We just measure the number of photons, the number of correlations, and divide by the average number of photons. So this was for a single atom. What do you expect in steady state for a large number of atoms? One well-known prediction is called the Ziegert relation. It says that G2 is equal to 1 plus first order coherence squared. Okay, so you get this prediction by just assuming that you have a bunch of emitters that have the same frequency, but that are phasing coherent with each other. So when you have like a big sum, you can reduce indices that are different, and then you get this 1 plus G1 squared. Okay, so this is for uncorrelated emitters. As soon as you observe this, you can say, okay, my emitters are uncorrelated. So this was verified, for instance, in cold atoms in many experiments. There is the group of Mathilde Hugbard and Robin Kaiser in Nice who have done experiments. In our case, what we did to try to see if at least we can find a case where this is verified, we take a cloud and we explode it. Basically, we make it very big. The atoms move apart from each other, so we try to kill completely correlations. And you see that we have G2 of 0, which is exactly equal to 2. And we see exactly 1 plus G1 squared. You have Rabi oscillation. This is the Fourier transform of the molar triplet. Okay? So we see very well this Ziegert relation. But then let's go to the interesting case where we had superradiance. We saw that we have correlations that appear in the ensemble. So we still drive the cloud like this. We wait to reach steady state, and then we measure G2. Okay. If we look perpendicularly to the axis, we measure 1 plus G1 squared. Okay. And this is expected, exactly as you expect that intensity is just the incoherent emission. You expect that you will respect the Ziegert relation. We have noisy data, but we don't see any departure from Ziegert. And the story is very different if now we look along the cloud axis. Okay, so you see here the prediction of Ziegert, and you see in red the experimental results. So if G2 is smaller than 2 and smaller than 1 at some place, smaller than 2 at 0 and smaller than 1 somewhere, you know that you violate Ziegert. There is no other possibility given the formula. So we see that we violate the Ziegert relation. This Ziegert relation assumes uncorrelated emitters, so okay, we have correlations, and let me try to pinpoint what is the level of these correlations for you. So we don't have any theoretical description of this problem. It's relatively challenging. We have 5,000 or up to 5,000 atoms in free space. So approximations are really hard to make, and so far we didn't, well, if anyone in the room is interested, of course, talk to me, but we didn't find someone yet. So nevertheless, we can still show what is the level of correlations that we have. And this is a very simple argument that was found by Giovanni. Is you can derive the Ziegert relation assuming Gaussian statistics. So Gaussian statistics, you take any high order correlation and you just express it as a function of first and second order correlators. Okay, so you have just two moments in your distribution. So you're saying that all cumulants above 2 are equal to 0 or connected correlations depending on your language. And when you do this, you obtain that for 4 observables, you have this relation, you apply it to the field to get G2, and what you get is that G2 follows this, this equation. Okay, so G2 is equal to 1 plus G1 squared plus these terms. These terms have to be there because a coherent state is a Gaussian state, and if you take a coherent state, then G2 is equal to 1 only if you keep these terms. So these terms have to be there, but in our experiment, actually, we can easily show that we have no average value of the field. There is no coherence because we measure G1, okay? And we see that, this term disappears. This term, probably if we were smart enough, we could eliminate, but I don't care too much because it's positive, okay? So if I see something that's going below 1 plus G1 squared, I know that I violate this assumption. And so actually, experimentally, we easily see that. We have 1 plus G, we have G2 that is smaller than 2, that goes below 1, so we know that this assumption is wrong. So we know that we have correlations inside the, so we measure the light, so we have correlations in the field that are non-Gaussian, but actually since the field is a linear superposition of the atoms, we know that the atoms do not obey Gaussian statistics. Okay, so we know that the theory is not that easy, indeed, because you have to have correlations of order higher than 2 in the theory in order to describe what we have. That's a challenge for you guys in the room to try to describe this. Maybe truncated Wigner works. I would be interested to discuss with anyone. And so we'll try to push a bit in this direction because actually this might be interesting, is the state of the light quantum. We have no proof of that yet, but at least we know that there are interesting correlations and who knows what they are. So we'll do our job. We are in principle a quantum optics group, so we'll try to measure the quantum state of the light. We have a recent work now on correlations during the decay. Okay, that's exactly what Arno showed us. So we can look at correlations now, not as the system is driven, but you drive it, you let it reach a given state, and then you look at how correlations evolve during the decay. So you can stop at a pi pulse, okay? So you just invert the system and look at what you get. And so in this case, what we see is during the decay, G2 is going down and reaching 1. So it doesn't start at 2 exactly. That's probably because we have already some superradiance as we drive, okay? We never reach 2, but we see a decay, and we see indeed that during superradiance, your second order coherence reaches 1, okay? So it's exactly what was observed by Arno in nanofibers. So you see that these are seemingly different systems, but in the end you get very, very similar physics. We can reach steady state and then let the system decay, and there in this case, we start from this value that was lower than 2 that I showed you before, but we see that there is no coherence that emerges. So, and in this case, we don't have superradiance during the decay. So there is clearly an effect. It's superradiance that establishes coherence during the decay. We looked also at 2-time correlation functions, exactly as we saw, and we also see that if you pick a given time and look what is the probability to emit another photon at a different time, you see something that is going smaller than 1, which is a signature of the fluctuation of the timing of the pulse and the fact that the pulse is shorter. And if you do the same thing, but now starting from the steady state, we don't see this. So we really here have a signature that you don't have any burst of superradiance when you prepared a steady state, which is strongly driven, which is correlated, but which is seemingly probably more of a mixed state. Okay. Excellent. So this was what I wanted to show you on the rubidium setup. Oh, I'm good on time. And I will now switch gears and try to show you what we see on the other setup, where we look at the internal degrees of freedom. We look at the atoms themselves instead of looking at the light. So the results that I'm going to present have been obtained mostly by Damien and Britton, who built the experiment in our lab. So we use dysprosium. Dysprosium is interesting for many different things. We picked it because it has all these different lines with different wavelengths, different line widths. So you have all the tools of atomic physics at your disposal. People have demonstrated single atom tweezers using similar transitions. So we just adapted these tools, and we managed to have single dysprosium atoms in optical tweezers that we can prepare an image. We can isolate a two-level transition and start doing physics in arrays of atoms. So we can prepare arrays of single atoms. So far, we're unfortunately not in the regime that you saw this morning. The distance between the atoms is still larger than lambda, but I want to show you today that you still have collective effects. We measure the atomic state, probably the same way as Marcus. So let me explain a little bit how this goes. You prepare an array, you prepare the atoms in the ground state, you do whatever time evolution by driving the system with light. At some point you stop, you have some population in the excited state, some population in the ground state, and then we use a very strong broad transition to actually depump very fast atoms in the ground state into other Zeeman states. We have an atom that has 17 Zeeman states in the ground state, so you can really remove it from the ground state of interest, and then you let the atoms decay and you re-image, and so the atoms that you image were in the excited state. Okay, so this is how we measure excited state population. This is how we project the atomic state, and with this we have single shot state readout with a fidelity that's 92%, and this is precisely what you expect because the pulse to depump is 100 nanoseconds. This is you need to scatter like 20, 30 photons to actually be sure that you remove the atom from the ground state. And in 100 nanoseconds, 10% of the atoms have decayed because the lifetime is 1.2 microseconds in the excited state. So if you take a longer lifetime, so if we take a narrower line width in the future, we can increase this fidelity to 99%. This shouldn't be a problem. So you see here, for instance, now same Rabi oscillations that I was showing you before, where we were measuring it in the light, but now we're measuring the atomic state directly. You see that you have very neat Rabi oscillations, and the decay is due to the excited state lifetime. So in this experiment, the first study that we did is motivated also by a paper by Francis to look at just a chain of atoms that you excite with resonant light along its axis. And in this case, actually, there is a very neat effect, is that when the light propagates, whatever the atom that scatters the laser light, actually, the radiation at the end is in phase, okay? So you have a constructive interference in the field that's radiated by all atoms upstream, okay? And so then this radiated field will interfere with the driving field, okay? So depending on the detuning, it will be either in phase with the driving field or out of phase with the driving field. So this is what is the consequence on the excited state fraction of the atoms, actually. If you are blue detuned, you know that if you're blue detuned with respect to an oscillator, it oscillates out of phase with the drive. So it means that the radiated field of the atoms upstream is out of phase with the driving laser. So it means that it will reduce the field that the atoms see at the end of the chain, and so you reduce the excitation. So you are in the shadow of the atoms upstream. You have a reduction of the excitation fraction along the chain. But now if you detune to the red of the transition, then the radiated field of the atoms is in phase with respect to the driving laser. So you have an enhancement of the field along the chain. You increase the probability to excite the final atoms. So you have, if you want, a lensing effect. It's a pretty tiny lens. It's 30 atoms that lens the field and increase the probability to excite the final atom. Okay, and so now it's quite nice that we have this single atom platform, because we can really resolve at the single atom level the effect of collective light scattering and collective dipole-dipole interactions. At the global level, what this means is that if, when you're red detuned, you increase the excitation, and when you're blue detuned, you decrease the excitation, it means that the fluorescence line moves, okay? You have a shift, okay? So you have if you average over the chain, you have a global shift of the fluorescence light. If you look at the excited state population, you have a global shift, which you don't have if you look perpendicularly, because perpendicularly you don't have this phase relation, so you have no shift. Okay, so we see a shift, and we can change with an AOD. We change the spacing between the atoms, and we can resolve very well how the shift evolves. Okay, so this shift actually you might have heard of before. It's just what people call the cooperative or the collective lamp shift. Okay, this is just the fact that you have a shift of the transition due to dipole-dipole interactions. So this shift here is measured in the very low excitation sector. So these atoms behave as classical linear dipoles. Okay, and we see a clear shift of the transition. But this shift is also important in the context of atomic clocks, where you do Ramsey spectroscopy, and if you have a systematic shift due to interactions, it might hurt the accuracy or precision, I don't know, of atomic clocks, and so it's important in the context of atomic clock to understand this shift. But in atomic clocks, you're performing Ramsey spectroscopy, so you put the block vector really on the equator. So you don't put a very small number of excitations, but you actually put 1/2 excitation per atom. And it was measured actually this year at GILA, the shift as a function of the area of the pulse. Okay, so here are the theoretical predictions. It's like a dashed area, and the data agrees very well with the prediction. So here on this axis, it's the cosine of so it's the vertical axis here. It's the cosine of the pulse area. Okay, so you have actually when you're doing Ramsey spectroscopy, you have an excitation dependent shift. So you see already that the picture is a little bit different with respect to just like a simple shift of the transition, because if it's just a simple shift of the transition, when you do Ramsey spectroscopy, it doesn't matter whether you excite here, here, or here. In principle, you always have the same shift. But here, you see that actually dipole-dipole interactions give you a shift that depends on how you excite your block vector. So the question that we had was, how do I connect these two things? How do I have one shift that in the linear regime is independent of excitation, because it's the linear regime, and in clocks, in Ramsey spectroscopy, actually depends on the excitation. So in clocks, what happens is that actually there's a prediction by Derek a long time ago that actually simply the shift in Ramsey spectroscopy is the shift that you would have in the low excitation sector times the cosine of the pulse. Okay, so that's why you have zero shift when you go on the equator, because cosine is equal to 0, and so you have no shift, and you see that the shift grows when you go away from the equator, and in principle you should reach the shift that we measured in fluorescence when you go to a very low excitation, and you should measure the opposite shift in when you excite almost all the atoms. But there's an interesting regime which is away from atomic clocks, which is our case, which is now what if you wait during your Ramsey pulses? Because we have spontaneous emission, we have collective spontaneous emission. That means that your block vector is going to go down between your Ramsey pulses. So you might change actually the shift that you would expect in Ramsey spectroscopy. And actually this is precisely what we observe. We observe that at short time we have an excitation that depends on, a shift that depends on the excitation that you put. But now as you wait, your block vector goes down. And what's interesting is that initially, imagine you're on resonance. So it means that your block vector, if you don't have a shift, doesn't rotate. So you start like this. It doesn't rotate, but then it starts to go down, and then it starts to rotate around the axis like this. Or if you excite above, it will rotate in one direction, cross the equator, and then start rotating in the other direction. Okay. So actually, this was absolutely not clear to me what was going to happen, and we were quite happy that we could actually relate what happens in Ramsey spectroscopy to what has been measured, for instance, in atomic vapors, etc., on the collective shift due to dipole-dipole interactions. So with this, I will maybe skip the summary in the interest of time, and I think that's all I wanted to say. Thank you.
This is very, very, very nice, very amazing. So for the last plot, when you put the lines, these are theory lines, or I mean, I think at some point you're going to go beyond in field.
Yeah. This is the spacing is about like 2 lambda. So we are doing purely mean field, and it seems to work pretty well.
I see, but you expect, I mean, as they go closer,
Yeah,
closer,
exactly.
you're going to
Yes, yeah. We would be very happy to see a departure from mean field. Yes.
So noisy.
Yeah. Because I mean, we do experimental theory. You know, we repeat the. yes, but yeah.
Right, very nice. I mean, in the first part, when you transversely illuminate, you said there is no coherence, but it's not totally true because along the propagation axis of the laser, you will always have super radiance.
Yes.
Why is this so much smaller than the other one?
You can calculate what's the emission rate because the optical depth in this direction, if you want, is 0 essentially.
Yeah,
because
all your dipoles radiate in phase.
Yeah. But because the collective, I mean, if you have Dicke superradiance in that direction, it beats classical superradiance imparted by the laser, if you want.
Yeah. Okay, thanks.
Go to lunch early. So.
Thank you.